Hey everyone, in this portion of topic 12.1 we're going to be looking deeper at Niels Bohr model of basically just the hydrogen molecule. Everything that we're doing here only deals with the hydrogen molecule. We get any of the more complicated atoms, including helium, then these equations and things do not apply in this form because it's just too complicated. So basically we're just dealing with the hydrogen atom. We're also going to look at Schrodinger's calculations for the energy of the wave nature of electrons when they're in an atom. So let's get to this and start looking. Now the first thing that we need to remember, we're looking at Bohr's model of the atom, is that MVR, let me get going here. There we go. MVR is equal to NH over 2 pi. This is basically an equation that Bohr has to describe the momentum that an electron has. He also gave it as L equals MVR. The momentum equals the mass times the velocity times the radius of the electron. He looked at the electron as basically just a big sphere, so, or I should say a tiny sphere. And so working with this, keep this in mind, we're going to come back to it. He wanted to look at the energy that the electron has as it's orbiting the nucleus. We got the nucleus, we've got the electron going around it, and it's going to have a certain momentum and an energy. And the energy, let's go, that's the radius. The energy is going to be equal to the kinetic energy plus the potential energy. So there's kinetic energy of it going around, its velocity, basically based on its velocity going around. And then there's the potential. The coulombic forces on this electron are trying to draw it in, and the kinetic forces are trying to keep it out. So where those two things are equal, we add them up to find out the total energy. Okay, so obviously kinetic energy is 1/2 mv squared, and the potential energy is given as, for coulombic forces, is given as Coulomb's constant times the charge of the electron squared over r. And this should look somewhat familiar to you because this is basically the charges, right? That, remember the minus k q1 q2 over r, and if these are the same, it's q squared. So we're basically looking at that's the potential energy. Okay, here's our equation. Now I'm going to do something strange here that is not going to be intuitive. This is probably the genius of Bohr, that he went in and did something like this. But the force acting on an electron, a coulombic force, is given by k e squared over r squared. I believe this is in the data booklet. Not, I can't remember if it's in the SL portion of the data booklet or the HL, but it's there. This is available to us in the data booklet, I'm very sure. And we can also list the force as mv squared over r. This is just a statement of the Coulomb, the momentum, force due to momentum, I guess you could say, the movement that is being put on this electron as it goes around the nucleus. So with these things being equal, I can rearrange this and I can get mv squared is equal to ke squared over r. You know, the r's here, we're basically just bringing this r over here, up here, and so it cancels out, and so we have ke squared over r. Now the reason why I did that is we have this and we have this up here. So I can substitute this into my velocity squared. And so I get for the energy. And so now this just puts everything in coulombic terms. I get 1/2, no, let me just, well, yeah, let me do it this way. 1/2 ke squared over r, Coulomb's constant times the charge of an electron squared over the radius of the molecule, I'm sorry, radius of the atom. And I'll just do this minus ke squared over r. Okay, so let me just rewrite this really quick. It's ke squared over 2r minus ke squared over r. Need to get a common denominator. So I've just put in 2 over 2 here, and that will give us minus ke squared over 2r, and that is energy. This is a key equation that that we use to calculate the energy of the electron. Okay, let's come back over to this. Now, again, Bohr did something that to me is not intuitively obvious, but that's part of his genius. So he just squared both sides of this. So m squared, v squared, r squared equals n squared, h squared, and n is just a quantized number, all right, this is a quantum, times 4 pi squared. All right, now then he's going to get this, he wants to get this to mv squared. We got mv squared in here, if you can see. And so that's just going to be n squared h squared over 4 pi squared, 4 pi squared r squared m. Okay, so this again is equal to this, so we can substitute that in. Ke squared over r equals n squared h squared 4 pi squared r squared m. And let's solve this. What we're doing here is we found the energy of the electron as it's going around. Here we're going to find the radius of the atom. All right, and so when we solve this, we get this down to r equals, and I would suggest you work through this to get to prove that what I'm telling you here is correct. R equals n squared h squared over 4 pi squared ke squared times m. All right, so you can get to this with, I skipped basically 1 or 2 steps and just came down here to what this is. But this is another key equation that is used. So here is the radius of an atom. And you notice that everything in here is a constant, including the mass. The mass of an electron is for mass, the mass of an electron at rest is constant. If it's moving, that's a different matter. But we're using the rest mass of an electron, and so we can calculate the radius of this electron. So let's do that. Let's see, or I'm sorry, this atom. So let's see what the size of this atom is. So R equals n squared. We're just going to go with the ground state here. 1 squared times 6.63 times 10 to the minus 34th squared, very tiny number, times 4 pi squared times Coulomb's constant, 8.99 times 10 to the 9th, times charge of an electron squared, times 10 to the minus 19th squared. It's a very long equation here, times the mass of an electron, 9.110, times 10 to the minus 31 kilograms. And so that's going to give us a radius, when you plug all that in, and that is a really fun thing to put into your calculator, but I suggest you do it. You learn how to do that. But you get the energy of, where do I have this written down? Right here is, I'm sorry, not the energy, the radius, 5.31 times 10 to the minus 11th meters. That is the radius of a hydrogen atom with its electron in the ground state. All right, and if you want to find out how much it expands, you just keep putting in the different quantum numbers here, okay? Okay, so that is the radius. Again, you see here that we have energy here that we want to figure out what it is. Now, this is, let's assume that we don't know what the radius of the atom is. What we need to do is we need to substitute something in here for R, so we don't have to rely on our calculation here. And by gosh, we have something right here. This huge number here. So let me actually go to a different color here so that it's obvious that we're looking at something else here. All right, so if I substitute in R here, I get E equals K E squared over 2. Now R here is inverted from R here. All right, so we would do n squared h squared down here in the denominator. In the numerator, we would have 4 pi squared ke squared m. All right, so the ke's can combine, so we actually get, let's see here, how do I want to write this? We get 4 pi squared, 4 pi squared, times k squared, e to the 4th. I'm just rearranging this here so it makes more sense. E to the 4th m over 2n squared h squared. All right, so basically we can get rid of that, make it this 2. So we have Oh, I'm sorry. This whole thing should be negative, right? Yeah, negative. So this whole thing should be negative, negative. And so that equals negative 2 pi squared k squared e to the fourth m over n squared h squared. All right, so energy, let's substitute in again. We've got nothing but constants here, and we're going to go with a ground state. Okay, so n equals 1 equals 2 pi squared times 8.99 times 10 to the ninth Coulomb's constant squared times 1.6 times 10 to the 19th to the fourth. Sorry, I'm running into my other here. Sorry about that. But and then 9.110 times 10 to the minus 34th. So squared, squared, squared to the fourth, basically to the 1, times n squared, which is 1 squared, times 6.63 times 10 to the minus 34 squared. So this is just some crazy numbers here, but it's pretty cool how this works out, because that works out to E equals minus 13.6 electron volts. Okay, now what you really get is joules. All right, you end up with E equals negative 2.1668 times 10 to the minus 18th joules, and then you convert the joules into electron volts. Okay, and you should know how to do that at this point, so practice doing that. I want you to run through, do these equations. I want you to practice what I just did here, deriving these equations, and then going through and getting these numbers, because on the test you could be called to do that. All right, but notice we have the n here, so if I just substituted in n squared here, then I would actually come out with minus 13.6 over n squared electron volts. So then we just put 1, 2, 3, 4. Okay, so that is the energy. We got the energy, we got the radius of a hydrogen atom at ground state. So I want to show you the interesting thing for the energy is, remember that when we observed let's see, in SL, we talked about how you take these different wavelengths that you observe the quantized light from, right? You get their wavelengths, and you figure out those energies, and you figure out the energy differences between the different orbitals, all right, the different packages that the electrons either absorb or emit, and you get these different energies. The really cool thing is, with Bohr's calculations, they match perfectly. The first level, E13, oops, sorry, getting ahead of myself here. There we go. E1, the first energy of the first level, the ground state, is minus 13.6 that he calculated, and the one that we observe is actually minus 13.6 electron volts. All the way up to 5. You look at these as you go to the different levels, N1 through N5. You see that N1 through N5 equals perfectly. So this is very significant. The calculated values equal the observed values exactly. Okay, so that is a very strong case that quantum mechanics is valid. This is one of the many, many proofs that they have that quantum mechanics is valid. So there's two ways to calculate the energies or to find the energies. You observe them and you find the differences between the different quantas, the different wavelengths of light that's absorbed or emitted, or you just calculate it and you have the calculations available to you there. Okay, all right, so that is diving deep into the Bohr model, where a little bit more insight in how he came up with his theory and where it goes. And just a second here. Sometimes this thing likes to move. Somehow I do something with my hand and make it move. All right, so let's move on to Schroedinger. If you all remember Schrodinger's cat, we're going to go and we're going to talk about not Schrodinger's cat, but we're going to talk about his theories on the different, let me see. I am getting not what I want here. I need to get a pin. I'm not getting a pin. Why am I not getting a pin? Okay, there we go. Okay, so Schrödinger looked at the hydrogen atom in two ways. He looked at it as a box. Boy, I'll get there. Okay, he looked at it as a box, and he looked at it as a circle, or as a sphere. But we'll work with it as a circle. All right, because that we're only looking at the cross section anyway. When he looked at it as a box, he looked at it as a one-dimensional box. Now, I try to pick, this is where quantum mechanics starts getting really weird for me, is how do you make a one-dimensional box? I thought boxes by definition were two-dimensional, but okay, we're just going to go with it. I can't really explain it myself. Okay, but let's go back. You remember in SL we talked about waves, basically fixed waves, right? Standing waves. And we stated that the length of we'll say a rope, the length of the rope that we were using for the different kinds of waves that we produced was equal to the wavelength. We could calculate from the wavelength. In this case, the first harmonic, right? These are harmonics. The first harmonic was equal to 1/2 the wavelength. The second harmonic is basically equal to the wavelength, 2/2 the wavelength. And the third harmonic, so first, second, third harmonic. And we can convert this to wavelengths equals 2L over 1. This would be 2L over 2. Again, I moved my thing. Let me try to get it back here. Yeah, I don't know why it is acting like this. Can't get it centered. We'll try to get it close. I think it's close enough. Okay, as 2/2. And then in the third harmonic, the wavelength is 3/2, 3L over 2. Okay, we'll come back to why that's important here. And well, let's just do it right now. So we can say the wavelength is equal to 2L over some quantized number, 1, 2, 3, or 4, right? 1, 2. Let's see. I keep doing this one backwards. I am sorry. This should be 2L over 3. All right, so there's our quantum numbers, 1, 2, 3. And all I did was just take these equations and rearrange them. All right, so the wavelength is 2L over 3. Now Schroedinger came along, and you look over here, and you see that he wrote what the wavelengths are for a circle, a wave that's in a circle form, basically. All right, it is 2 pi r for wavelength 1, for wavelength n equals 2, it's 2 pi r2, and for wavelength 3, it's 2 pi r3. That should have been 2 down here and 2 here. Sorry, 1. This is really messing it up for you, but there it is. Okay, so that's going to come in. We'll use that here in just a little bit. Okay, now what Schroedinger was saying was that you've got a wave of an electron, the wave function of an electron. If you remember, he's stating that the particles, electrons, have a wave function, and their wave function acts as if they are standing waves. All right, so we're going to look at those standing waves as if they're in that one-dimensional box and as if they're in that circle. Okay, so if you remember, we can also say the wavelength of the electron is h over mv. This was the standard, the basic equation in our data booklet for the wavelength, the de Broglie wavelength. All right, and that's who we're talking about, is the de Broglie wavelength of these things. Okay, so we also know that it's equal to 2L over n because it's a standing wave. So it goes 2L over n. So what I can do is I can just cross multiply this and say that Hn, or NH, equals LmV. All right? Now if I want to know what the velocity of that wave is, I can just write it here, equals NH over Lm. All right, so this is cool. I've got a velocity, so what does that mean I can do? E equals 1/2 mv squared. The kinetic energy is 1/2 mv squared. So I can find out what the kinetic energy of this wave is. This wave will definitely have a kinetic energy. So when I substitute that in, I substitute velocity in for here, I get 1/2 m times n squared h squared over L squared m squared, right? Did I get this right? Oh, I forgot the 2 in here. That's what I was forgetting. So it's 2Lm. So it's 4 L squared m squared. So there was a 2 here that I did not put in. All right, let me see where it was V times 2 LMV. Yep, okay, so that works out. All right, so the I actually get M here. I have 1/2 times 4, so E equals n squared h squared M down here. All right, n squared h squared over 8 L squared M. Make sure I've got everything right there. N squared 8 L squared M. All right. So this is the energy of an electron in a hydrogen atom. If you treat it as a standing wave That's just basically in a one-dimensional box. Now we can do the same thing with the circle. We have lambda equals 2 pi r, right? That's what Schroedinger gives us. This is what the energy of a wave in a circle would be. And again, that is equal to nh over mv. So again, let's solve this for velocity. So mv equals nh 2 pi r. Let me see here. I'm looking. Did I do this right? No, I did not do that right, did I? Okay. I need to go back to algebra class. Okay, so 2 pi r mv equals nh. So velocity equals nh over 2 pi r mv. So again, I substitute it in there, and I get energy equals 1/2 m times n squared h squared 4 pi squared r squared m squared, and that's it. Don't know why I had the v in there. All right. Once again, the masses cancel out. I have 2 times 4, so E equals n squared h squared over 8 pi squared r squared m. Make sure I got that right. 8 pi squared r squared m. Yes. And there is the energy for this wave as we've derived it. Okay, so we have it if you want to solve it as a box, and we have it if you want to solve it as a circle. So it depends on, this is probably the most common one, the circle one is probably the most common one, because really you treat an atom as being more of a sphere than you do a box. But just so you know how to do both of those. Now, what I'm going to start from here is something you do not need to really know other than conceptually, because you can then take the derivatives of these and you can come up with some very interesting things. I'll show you. You basically come up with the shape of the orbitals as we learned them in chemistry, and that is based on this equation. E, the kinetic energy plus potential energy of the electron times, it's called the wave function, the wave particle function. I'll explain that here in a second. Is the energy of that wave particle function. So capital psi, this is the Greek letter psi, is really both the wave and particle properties of, in this case, an electron, but of any particle, of a particle. And they don't give us exactly what that is. It doesn't really matter in our case. We just need to understand that is what Schroedinger is using for his equations, and these are the basis of those. So these are the wave functions, and we know the particle functions basically, but they combine that into one equation. But that's outside the scope of this class. All right, so let me just show you this though. When they do the derivatives, they get the, basically they get the radius, the what are the different things, the velocities, the momentum, all that kind of thing, everything, they add it all together in that equation, take the derivatives and things, and you get the different orbitals. Okay, These are all what the different orbitals look like, and this is why you see them in chemistry where they say the first one's a circle and the second one, the p orbital kind of looks like that, and I forget what they say what the rest of them look like, but that's where they're getting those kind of shapes from, is from Schrodinger's equation there. Okay, so that is a deeper look at Bohr and his model of the atom, and Schrödinger and how he came up with the shapes of the different orbitals, and that is based directly on the de Broglie wavelength, de Broglie wave property of matter. All right, we have one more lesson to go in this topic 12.1, and so I will see you back then. Work on the worksheet through, let me see here, through problem number, it looks like all the way through 14, yeah, through number 14. Okay, so you should have already done 1 through 7, and now you can do 8 through 14, and we'll work on the rest of them next time. We'll see you then.